Now imagine students, let's take an example of solids. Let's say this pen. This is composed of particles which are rigid. This is an electric iron. What is going on inside? That is what I am trying to show here. So now imagine this is normal temperature. The contact is here. It is maintained with the circuit. Now let's revise again, students. What is internal energy? The internal energy of a substance is the boiling and evaporation. So many times in your previous classes also you have discussed that. But okay, students. So now let's talk about this very quickly. Solid. Let's say this is in degrees Celsius. Hello students, welcome to the third part of thermal physics. Students, now two parts have happened. We have discussed a lot about thermal physics and I hope the clarity is there. One thing, but we have always talked about the conclusion that thermal energy has been transferred, something has changed temperature, something has changed state, but we never talked about how this transaction happened, how this transition of heat happened or thermal energy happened from one substance to the other, or from one object to the other. So it is like a banking transaction. You make a transaction, somewhere it is a credit, somewhere it is a debit. So someone gains energy, someone loses energy. But how this happens? What is the mode by which heat gets transferred? That is what we are exploring today. So transfer of thermal energy. A lot of diagrams you can see. How are we heating up water? Okay. Hot and cold, two bodies interacting, heat flowing, thermal energy flowing from hotter substance to colder substance. How does that happen? Okay, the sun, how are we getting heat from the sun? Fire. So all these things we will discuss today. It's going to be a short and sweet class because it's majorly the qualitative discussion, no major numericals that you can get here. Alright, so put down the heading, transfer of thermal energy. Alright, so conduction. So the first mode that we are going to discuss is conduction. Imagine it's a very chilling winter season and you touch the bicycle grip to ride the bicycle. It feels all right, right? So you ride the bicycle, it's all fine. But what if you touch the metallic part of the bicycle? That feels way cooler. So if I may ask, which is at a lower temperature? Is it the grip, this rubber grip? Or is it the metallic part? So think about it. Which has a lower temperature, the grip or the metallic part? So most of you might be thinking that of course it is the metallic part which is at lower temperature. But what if I tell you that both are at the same temperature? The grip and the metallic part both have the same temperature. There is no difference. But then why does that metallic part feel much cooler? That's because when you touch it, it takes heat out of your hand. It takes thermal energy out of your hand way quickly. But you need to touch it to feel it. That is what conduction is. In conduction, you transfer heat from one substance to the other by bringing them in contact. And what happens then after that is basically the transfer of energy from one particle to the other, then from second to third and stuff like that. So let's understand how it goes. But one thing that is surprising, that both are at the same temperature, still you feel that heat is taken out of your hand at a quicker rate from the metallic part. That means the conduction is better in the metal and it is lesser in the insulator part, that is the rubber or non-conductor. Okay, so conduction is the transfer of thermal energy through solids mainly, right? That is why we were talking about that contact. Okay. The thermal conductivity of a material is dependent on how quickly thermal energy is transferred from the hotter end to the colder end, right? In general, metals are good conductors of thermal energy. So let's understand what is happening. Imagine this is the lattice chain. Okay, in any conductor, it can be a solid rod. Now, when you heat up one end, this will start vibrating more vigorously. Then it will transfer its energy to the next particle. Why? Because it's like vibration happening and the particles are getting transferred, like energy is getting transferred to the next particle. So it is in a way this ripple effect that is, proceeding in a way like a domino effect. Okay. So energy gets transferred to the next particle, to the next particle, to the next particle, and that is how conduction happens. That is going to happen in all solids. But now think about metals. So in metals you have free electrons, delocalized electrons. So these electrons can move throughout the space of the lattice. So when energy is supplied, they move in bulk and carry the heat. So that is why metals, they are good conductors of electricity, but they are also good conductors of heat. Okay. So in general, metals are good conductors, while non-metals such as glass, plastic, wood, air and water are bad thermal conductors. So what happens in conductors? The particles won't move themselves, they will only transfer their energy to the next particle, and that is how thermal energy gets transferred. Alright, make a note of it, then we move forward. Okay students, so the next thing, so direction of thermal energy, this is a burner, this is a solid rod. This is an experiment which is very often there in the questions, so keep that in mind. So this is some wax, and you just want to test different materials, how good or bad of thermal conductors they are. So what you can do is you fix a given amount of wax and a drawing pin, and you wait for the wax to melt and the pin will drop. So let's say you do this experiment with metal A, then you take the same dimensions and you repeat the experiment with a metal B. Quicker the pin falls, that means the better the conductor it was, isn't it students? So that is about how you can test or compare thermal conductivity of various substances, but it's obvious that it will flow from hotter region to the colder region. Alright students, so the next thing is convection. So convection is the transfer of thermal energy in a fluid. So fluid, when I say fluid, it is liquid or gases. So now the particle will themselves move in bulk, okay, and that is called a convection current. What do you call that? Convection current, okay. So due to a difference in the density, keep that in mind. So what triggers convection is the difference in the density. Let's understand how convection works, how it is different from conduction. Okay, so imagine you are heating water here. The first stage is through conduction, heat will go to the water. Why conduction students? Because this is this metal vessel, so heat will go through this metal, that is conduction on the first step. Now the water particles here will start gaining energy. When they gain energy, their density decreases, okay, so they become less dense. The spacing between them increases, they become less dense, they start to rise, okay, they start to float upwards, right? And what happens at the same time, the denser water, the denser particles, they start moving down, okay. So this is the denser, so this is the cooler water and this is comparatively the hotter water. So imagine after some time when you touch the water at the top, you would feel as if it is heated up. But is it the water heat that is being transferred by conduction? No, the particles themselves have moved. So when the particles themselves move, that is what we call as convection. But this freedom of movement of the particle is only there in fluids, it is not there in solids. That is why convection is only associated with fluids. There can be many examples. Imagine an air conditioner in your room. You would always have it at the higher part of the wall. It won't be at the lower part. Why? Because hotter air being lighter will always rise and we want it to cool down, isn't it? So that is why a convection current is set up. So whatever a hotter air is, it rises, the air conditioner will cool it down and then it will come back to the lower state, right? So this convection current is set up. This is what we call as convection current. So this is the hotter thing that will rise and this is the cooler thing. So I hope you are understanding how convection works. There's one more example. We have talked about specific heat and everything. So in the daytime, the land heats up more, the air rises and this high density air starts flowing from the sea to the land. This is what we call as sea breeze, okay, and in a way it also has a role to play in deciding the waves. In the night time, you do understand that water has a higher specific heat capacity. It does not get heated up or cooled down that easily. So in the night time, the land becomes comparatively cooler while the water is still hotter. So the air here rises and a cool wind blows from the land. So when it blows from the land, this is called the land breeze. When it blows from the sea to the land, that is called the sea breeze. Okay, so there is always a wind blowing near the beach areas. That is the reason behind that, this density difference of air above the land and above the sea. So I hope you are now clear what convection is and how it is different from conduction. All right, copy down the important stuff or the definition and then we move forward. Alright students, now let's talk about the major source of heat for us, for thermal energy for us, and that is the sun. Now imagine, be it conduction or be it convection, they need particles to transmit that heat. They need particles, whether it is conduction where there is a chain of particles, or convection where the particles are moving themselves. But imagine, this is sun, this is the atmosphere. The atmosphere is almost in this 10-20 kilometers. But sun is further, way further than this. So this whole region is air free. There is no air, there is no medium. This is obviously vacuum. So if this is vacuum, how can heat or thermal energy flow from the sun to the earth? That is the major question. So that is happening because of radiation. Now when we talk about radiation, radiation are of different types. These are electromagnetic radiation. We will discuss that, but first let me talk about the definition. Thermal radiation is the transfer of thermal energy in the form of invisible waves called the infrared radiation, which can travel through a vacuum. Unlike conduction and convection, infrared radiation can travel through a vacuum. Okay, so these are infrared. So the sun spectrum, the spectrum that we get from the sun, which consists of visible light, you might have heard of it, infrared, microwaves, radio waves, ultraviolet, there are a lot, but the most heating effect is of infrared. Keep that in mind. So the energy is being transferred in the form of radiation. That does not need medium. Light does not need medium for it to propagate. Okay. Alright, so let's look at that now. So all objects absorb and emit infrared radiation. This is very, 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 very important. Even we are emitting infrared radiation. That is how night vision cameras work. If there is no light, we are not reflecting anything. Still we are emitting some radiation. The particles of our body have some thermal energy. We are continuously radiating. We are continuously emitting. So there are two things that is happening with any object. It is emitting due to its own energy and it is absorbing due to the surroundings, right? So in a way, if you are sitting in your room, the walls are emitting, the floor is emitting, the ceiling is emitting, and you are absorbing those radiation. At the same time, you are emitting also. So emission happens because of your own particles energy and absorption happens because of the particles surrounding you. They are emitting and you are absorbing that. These are all radiation. So what is the electromagnetic spectrum? Radio waves that you use in mobile phone communication, microwaves that you use in microwave ovens, right? Then infrared, these are the main source of heat. So microwaves also slightly have an heating effect on water specifically. That is why microwaves are used to heat up something when you want to supply heat to the water particles of that food object. But right now we are not discussing that, we are focusing on infrared. Then of course there is visible light. So when we are moving towards this end, frequency is increasing. Frequency is increasing, okay? And when we are moving at this end, wavelength is increasing. Don't worry if you have not heard of these terms. We will talk about them later. Okay, so we are right now focusing on infrared radiation. These are what we call as heat waves. Okay, so visible light, ultraviolet light, X-rays, and then finally is gamma rays. All right, now let's talk about what factors affect the emission and absorption of thermal radiation. This is very important. First is of course the surface temperature. Imagine something in your room is hotter and something is colder. So for example, a hot cup of coffee and a cold drink. Who will emit more? Whoever has more energy. So it is going to be the hot cup of coffee that is going to emit more. Keep that in mind. So the first thing, the amount of infrared radiation from a surface depends on three factors. First is the surface temperature. I want to discuss this first. First is the surface temperature, because more temperature means more energy in the particles and therefore they are emitting more. Alright. Second is the surface area. If something has a higher surface area, more particles on the surface, more radiation they are going to emit, isn't it? Third is the surface color and the texture. Okay, surface color and the texture. So now let's talk about that. Imagine this is an object. It is absorbing radiation. So if it is black colored object, for example, then it will have a tendency to absorb more. Okay, so black will absorb more. Black will absorb more. On the contrary, if it is a white colored object, then it will absorb less. Why will it absorb less? Because it will reflect more. It will reflect. So when something is white in color, that means it is reflecting more. So if it is reflecting more, it will absorb less, isn't it? So black will absorb more, white will absorb less because it will reflect. So whatever radiation it is receiving, it will reflect that. So who is a better absorber? Students, it is the black color. Who is a better reflector? It is the white color. So white is less absorbing, black is more absorbing. That is one side of the story. Now who will emit more? Who will emit more? So it is just like who will emit more? Whoever has more energy. So if black will absorb more, it will have more energy. So if black has better tendency to absorb, black will emit more as well. Black will emit more, while white will emit less. So imagine, students, whoever is a good absorber is always a good emitter. I am not talking about reflection here. So whoever will absorb more will also emit more because it will gain energy easily. So it will emit more as well. So now think about it. I have black dull. So this is dull black, isn't it, students? This is like shiny black. Can we call it like that? Now this is dull white and this is like shiny white. Right, students? Think about your answers. Who will absorb most? Answer is going to be this. This will absorb the most. Who? Dull black, because it's not reflective. It is like absorbing. It is dull. It is not smooth. It is rough. So it will absorb more. Then shiny black, then dull white, and then shiny white. So this is the order in which they will absorb, and this is the same order in which they will emit. But reflection is just the opposite. Who will reflect the most? Shiny white. Who will reflect the least? That is dull black. Students, again, don't get confused between emission and reflection. So whoever is a good absorber is a good emitter, right? But a bad reflector. So dull black is the best absorber. It is also the best emitter, but it is a poor reflector. All right. So I hope you are understanding. So three things that will decide the radiation emitted. First is the surface temperature. Second is the surface area. And third is the texture or the color. Right, students? Next, let's take an example. How does emission and absorption affect the temperature of an object? So let's say this is an ice cream which has a temperature of -10, while the surrounding temperature is 25. So it is in a transition mode. It will absorb more but emit less. So the amount of emission is less than the amount of absorption. So it will absorb ultimately. So incoming is more and outgoing is less. Why? Because outgoing will be decided by its own temperature, while incoming will be decided by the surrounding temperature. So outgoing is more, incoming is more and outgoing is less. Okay, that is why ultimately it will heat it up. It will get heated up. So its temperature will rise. Right, students? Are you able to understand? Now a hot cup of coffee which might be at 80 degrees Celsius while the surrounding is 25. What is going to happen now? So emission will happen as per 80, but absorption will happen as per 25. So who is more now? Emission is more than absorption. What does that tell you? If emission is more than absorption, then there is a net outgoing and the temperature will fall. Imagine a chair in your room temperature is 25, the chair is also at 25. So is it now absorbing or emitting, or is it doing nothing? Answer is it is doing both the things, but the emission rate and the absorption rate both have become equal, and that is why its temperature will remain constant. Right, students? I hope you are able to understand how radiation is working. Radiation is electromagnetic waves which do not need medium to transfer. Okay. All right. Next thing, greenhouses are used in cold climate. So I just took it to give you a fair idea of how we can make use of these infrared radiation. So there are very cold climatic conditions and you want to do farming over there. So this is what you rely on, greenhouses. So what does greenhouses do? They trap the sun's energy while they are transmitting through the glass. They lose energy and they convert into infrared. Those infrared gets trapped inside this, and in spite of, let's say, outside temperature is minus 30, you would be able to maintain a temperature of 10 degree, 20 degree inside the glass houses. So this is called the greenhouse effect. In fact, some gases are forming a jacket over the atmosphere. That is what we call as the greenhouse effect on the earth, which is causing the global warming, isn't it? So greenhouses are used in cold climates to trap thermal energy. The temperature of a greenhouse is higher than the temperature outside. This enables plants to grow when it would normally be too cold for them. Right, students? So just to give you an idea how greenhouses work, all the radiation, let's say ultraviolet, visible light, when they pass through glass, they convert into infrared, and infrared gets trapped because they are unable to penetrate the glass. So in a way they keep accumulating, and these infrared radiation will keep accumulating and raising the temperature. All right, students. Last, let's do one question and that will be all. Okay, some water in a glass beaker is heated from below as shown in the diagram. Name the process by which thermal energy is transferred through the glass. So answer is going to be conduction. Then throughout the water, then the answer is going to be convection, isn't it? As thermal energy is supplied, the temperature of the water begins to rise. Although the supply of energy remains constant, eventually the temperature becomes steady. This is very interesting, students. You are providing heat, still the water is not going above 80. Why is that happening? That is because the outgoing heat is equal to the incoming heat. So this is happening because outgoing thermal energy and incoming thermal energy becomes equal. Or you can write thermal energy absorbed and thermal energy emitted becomes equal, and equilibrium has been attained, and that is why it is unable to go beyond 80, isn't it? The rate of energy supply is increased. Now we are increasing that. The temperature of water begins to rise again, but eventually becomes steady at a higher temperature. This time many bubbles are seen. So of course it is boiling now. What is now happening to the water? It is boiling. What gas do the bubbles contain? It is of course steam. Steam, right, students? Air, hydrogen, oxygen, no, it is vapor form of water, that is steam. Right students, I hope you are able to build up confidence now after these classes. Thermal physics is comparatively an easier unit students, and you should do really well in this unit, because it, as compared to the force energy unit, there you had a lot of numerical problems. Here you have very limited of them, and that too very streamlined. So I think you should be able to do them after all these classes, after watching all these classes. Don't worry if you are still unable to apply the concept, because next now we are coming up with the topical PYQs, and after that we will, of course, you have our past paper solutions. So all these things should help you to get you the desired result. Thank you so much for your time students. It was lovely teaching all of you, and we'll keep interacting like this. And do let me know in the comments what else you want us to do. We will try to achieve that as well. How do you want us to improvise? Your suggestions are always welcome. Alright students, thank you, and I will see you soon. Bye bye.
If you enjoyed this video, please don't forget to like, share and subscribe to our channel.